In this second section, I'd like to try to be a little bit more precise about what I mean by mathematical physics and what types of problems can be regarded as problems in mathematical physics. Clearly not all mathematical problems in pure mathematics, are of interest to a physicist. So intrinsically, a problem in mathematical physics is not a problem in pure mathematics. Nor is it true that all problems in physics, in theoretical physics, are of a mathematical character. There are many problems in physics, and if you go to a reference to open problems in physics, you'll get a list more or less similar to the one I'm going to give in just a moment. But if it's theoretical physics and it's on the vanguard of new research, often the problems are not particularly well formulated, and so they don't give rise to rigorous mathematical questions. The exceptions might be topics like general relativity and quantum gravity, where there is a mathematical formulation that can be studied. One of my favourite quotes in mathematics, physics, is the quote by Wernher von Braun, the rocket scientist, who said, "Basic research is what I'm doing when I don't know what I'm doing." So, most important unsolved problems in theoretical physics. And the problems tend to be theoretical physics, they tend to be problems in the small and in the large, where there's a lack of observations and experiments, and so theoretical results play a more important role. This is a typical list. Problem of quantum gravity, formulating a theory that unifies quantum mechanics and GR. Foundational problems, interpretational problems in quantum mechanics. Particle physics, tuning problem, that's kind of like the philosophy behind quantum mechanics, problems concerning the philosophy behind, and problems of in cosmology, which is based on general relativity, which is a well formulated set of differential equations. So, in general, problems in mathematical physics will not include problems where the basic underlying physics is not understood. The theory has to mature sufficiently that a precise, rigorous mathematical problem can be posed. So, as I said a little bit earlier, those theories, Navier-Stokes, Maxwell equations, Yang-Mills equations, general relativity, where there's a well-formulated set of differential equations, you can start asking rigorous problems. Rather than being too semantic and giving a definition, it's illustrative to look at what types of problems people are interested in, and I think this is nicely illustrated by a set of problems by Barry Simon, which I'll talk about in just a moment. There are a number of problems, and various people have put forward problems in various disciplines, which would go under the banner of problems in mathematical physics. There's a few commented there. There's a few lists that are referenced. Let me just mention one or two. The DARPA mathematical challenges were proposed, which are very heavy in applied mathematics and theoretical physics, and they consist of problems in open problems in classical fluid dynamics, such as the Navier-Stokes equation, their use in understanding shock waves, turbulence, and solitons. All of these can give rise to rigorous mathematical questions, and also problems in looking at complex fluids, things like analysing liquid crystals, and the so-called Langlands program. There are a number of other fields for which you might claim there might be open problems. Let's call them more speculative topics. Work in the brain, stochastic problems, problems in theoretical biology, biological quantum theory, the mathematics of quantum computing, of which we have a very strong group here at Dalhousie. So there's a number of problems that, shall we say, might be associated with very modern areas of physics, although I'm sure my colleagues would claim that there are some very precise mathematical questions in quantum computing. There are also even more speculative questions to do with studying, let's see, consciousness, the brain, what else have we got? Some philosophical aspects of cosmology, problems in ethics. Probably most of these problems would not fall under the umbrella of problems in mathematical physics. But I've referenced an article here by Allen and Lidstrom, which talks about some of these problems in theoretical physics in more modern contexts. In the same way that certain characters in pure mathematics have influenced the field, there are a few people that I might mention that have influenced mathematical physics. Perhaps first and foremost would be Ed Witten at Princeton. He's the only physicist to ever be awarded the Fields Medal, which is the highest honour that you can be awarded in mathematics. As you can see, it's like the Mathematics Nobel Prize. Mathematicians that greatly influenced physics would be Roger Penrose, Michael Atiyah, Stephen Hawking. These are mathematicians, although their work may be known in physics, particularly Stephen Hawking. Stephen Hawking in his later life probably focused more on physics than he did on mathematics, but he was a mathematician by training, and his original research was in mathematics. These people have influenced physics greatly. Atiyah's student, Simon Donaldson, has been very influential more recently, and he has basically begun several fields of mathematics which have applications to physics. Here I've just mentioned here the application of gauge theory. And famous mathematicians like Yau and Schoen, basically analysts, differential geometers, who have become interested in problems in general relativity and mathematical physics in general. Just a little note here. One area of quantum gravity that's particularly popular is string theory, and it's strange that most string theorists are now in mathematics departments and in physics departments. So Simon's problems, Barry Simon's problems, set of open problems, 15 problems, who is a well-known mathematical physicist. The questions are varied and will be in topics like fluid mechanics and stochastic equations, stochastic differential equations. Just mentioning one or two. These two problems here are in fluid dynamics. There's one question in ergodic theory. In statistical mechanics, it's observed that systems of bulk systems quite often rapidly approach an equilibrium state. And it was originally believed that this could be proven that the classical dynamics in general tend to an ergodic state. However, there's a famous theorem, the KAM theorem, in dynamical systems about the persistence of something called quasi-periodic motions, which implies that many systems are not ergodic. And then there's some problems in renormalization theory, Renormalization theory was introduced by these people here, particularly Wilson, which describes critical phenomena, which can be used to describe something called universality in physics. And this was this topic was attempted to put this topic on a mathematical, more mathematically rigorous framework. Various people have put forward problems in general relativity, particularly Yau, which we just mentioned. Penrose has put forward a series of questions, and a little later, somebody who's perhaps not as well known in the mathematics community is Bartnik. These questions here were kind of more sub-problems which needed to be solved to pose the more grandiose open problems that we would now recognize. And Bartnik actually stated these theorems in a more general sense. I'm not going to say anything more there. There are various problems, and of course in general relativity, because the equations are written down in terms of differential equations, well-posed differential equations, lots of problems can be posed in a rigorous fashion. Okay, I'll stop there.